it says, finding the slope of a tangent line and finding the equation of a tangent line. So I can ask you guys a question. I'll probably ask you this 500 more times. I'm probably exaggerating a little bit, but let me ask you this question. I think I've already asked you it once. What are the two things you got to have to find the equation of a line? Okay, 2 points would work. I agree with you. But we're talking about a tangent line, so I think I would go with a single point and a slope. That makes sense? And so, you're right, of course, Christine. You're right. But since we're talking about tangent lines, let's go with a point and a slope. And I would like to kind of illustrate what I'm talking about with that little blue graph on the right. So we're going to be doing number 8. Number 8 deals with the function f of x equals x cubed minus 9x. And this graph over here on the right is actually a graph of x cubed minus 9x. Okay, so I want to demonstrate a couple things with that graph. We are being asked to find the equation of the tangent line at x equals 1. So as I focus on that curve, wouldn't it be fair to say that x equals 1 is like right about there? I put a little red dot where I was talking about. Do you see it over there? X equals 1 is approximately right there. Okay, so here is what we are actually finding. Excuse me. We are finding the equation of the tangent line. And so this might take me a couple of tries, but here's going to be my attempt to draw. That's actually pretty good. I'll go with that. Yeah, usually it takes me like 6 tries. Yeah. Or maybe 5. But yeah, that worked on the first try. So that is an example of what we're trying to find. Like that is a tangent line. It intersects the curve just in that one point, at least locally speaking. Is that better? Is that good? Okay. And it matches the slope there. So let's talk about a little terminology. Do you guys know what to call this point right here, the point where the line and the curve intersect in that one point? What do we call that point?
Point of tangency.
Nice. Point of tangency. Were you guys saying it back there too?
Yeah.
Point of tangency. So really simply, that's where the tangent line intersects the curve. And it's a crucial point, right? It's an important point. And so when we go back and kind of circle back to what I asked you guys at the start, what are the two things you got to have? A point and a slope. That's oftentimes your point, right there. The point of tangency. And then let me ask you maybe just one other way to think about this. If that's our point, if that's the point we're going to be using here, and we're looking for the slope of the tangent line, what am I really saying? Slope of the tangent line is really?
Slope of the point of tangency.
Right? And so I think somebody said something else. It's the derivative, right? Specifically dy dx, right? It's the derivative. And so that's what we're going to try to do here. So let's take a look at A. We're going to try to find the equation of that line. And so I've got to find those two things. I've got to find the point of tangency as well as the slope of the tangent line. So let's go ahead and do the point of tangency first. Don't I already kind of know half of the point of tangency? What do I know? It's going to be 1 comma something, right? We know x is equal to 1. We don't know what y is yet, but we can figure it out pretty easily. So I would say something like this. F of 1 equals, and we just plug that 1 in for x. We do a little arithmetic, and we get a number. What do you get? -8, yeah. F of 1 equals -8. So we're trying to find the point of tangency here. So if you wanted to write it a little bit differently, you could write 1 comma -8. That would be your point of tangency. Of course, you could write it in function form or ordered pair form. It's the same thing. So we found half of it, right? Just like that, we found half of it. But now we got to find the slope of the tangent line to go with that point of tangency. So Doug, what should I do if I'm looking for the slope of the tangent line? So let's go back. Let's break those words down. This is, guys, the question here is really important because if you say find the slope of the tangent line, you're kind of like, gosh, I'm not even sure what to do with that. We need to talk about that, right? So think back at what we described at the start of the class. Slope of the tangent line. What am I really talking about? Derivative. The derivative. And specifically, because a derivative, as we talked about with 15-minute ride, could be like dv dt, right? So specifically, we're looking for what? F prime. Okay, I could go with F prime. If we wanted to use y notation, maybe like dy dx. But let's go with F prime. So what is that, Doug? F prime of x is equal to what?
Isn't it?
Yeah, a chance to practice the power rule a little bit. Yeah, look back if you want to.
Isn't it just like f of x plus h? Or no?
Oh, let's not do the definitional derivative, Doug. Please, don't do that to us. Let's do the power rule, right? It's okay. It's okay. So let's review really quick. If you need to, go back.
The 3 from the power thing.
Yes. So what would that look like for this one?
So that would be 3x squared, yeah.
Minus
9.
minus 9. So if you need to, go back and watch that. Doug, if you need to go back and watch that 2.1 video or 2.2?
Yeah.
2.2. Do it.
Single practice, that's it.
Okay, yeah. Whatever you got to do, either way. Okay, so there is f prime of x. I want to be really clear about this. F prime of x is the derivative, it's the slope of the curve at any point. So let's do a couple of examples, right? Let's look back at that curve over there, and let's say I wanted to do let's say I wanted the slope at 0. Yeah, slope at 0. What does the slope at 0 look like to you guys? Is the slope at 0 on our blue graph, is it positive or is it negative? Pretty obviously negative. So if I wanted to find the slope at 0, which ultimately that's not what I want to try to find, but I could, I'd go f prime of 0, and what would I get? Does that make sense with what you observe on the graph? Okay. What if I wanted to do something else? Instead of f prime of 0, I wanted to do like f prime of, I don't know, negative 3. I wanted to find the slope at negative, so that's over here, right? That slope looks like what? Clearly positive, I would agree. So if we did f prime of negative 3, what would we get for that? $18. Yeah. So does that make sense with the graph? Pretty steep positive slope. So hopefully that's all making sense to you as far as just looking at the graph and kind of making a judgment. Far from an exact science, but at least the positives and the negatives agree. We don't really care about 0 and negative 3. What do we care about? 1. We want to know the slope of the curve at 1. So instead of doing all that other stuff, I'm going to do f prime of 1. And what does f prime of 1 end up being? Negative 6. Good. Okay, so I've got the slope of the tangent line. I've got the point of tangency. All we need to do now is put it together. I happen to be a big fan of point-slope form of a line. You might like slope-intercept form or some other form, I don't know. The reason why I'm a fan of point-slope form is because it's really fast and it's really easy if you just plug things in. So here is point-slope form just in its basic form. It's y minus the y-coordinate equals m times x minus the x-coordinate. And so for this one, it would look like this. I'll put this in different color. Let's go with y. Wouldn't it technically end up being y plus 8, right? Minus a negative. So it'd be y plus 8 is equal to slope is negative 6, x minus 1. And that would be it. If you wanted to transform that over to slope-intercept form, of course, that's fine. But I think that's really easy.
Leave it like that?
Oh, totally. Please do. Unless you're otherwise directed, just leave it like that. Because that is definitely an equation of the tangent line. So, okay. Let me ask you guys one other question here. I'm going to erase all this junk over here on the graph for just a second. And I want to ask you guys, we're going to move on to B here. Sorry, did you have a question?
No, I'm questioning my colorblind.
Yeah, he's colorblind, so I'm explaining.
Sorry. There's somebody in my other class that also, yeah, it's colorblind. Sorry? No, it's Dylan. Dylan, yeah. He did the same thing as Dan is doing right now. He's like, what? There's different colors up there? I think one was red and the other one was green. He's like, they look the same. I'm like, sorry. Okay, so let me ask you guys a question about the graph. I don't know what to do about that. On that graph over there, the blue graph, how many horizontal tangent lines do you think there are on that particular graph? There's 2. So if we were to try to illustrate those, I'd say there's one of them right there roughly and one right about there. Those are the 2 horizontal tangent lines. So just looking at the graph, just like eyeballing it roughly, what would you say are the x-coordinates for those horizontal tangent lines? Yeah, plus minus 2 seems like a pretty reasonable guess. So what we can actually do is we can find the exact location of those using a little bit of math. And here's how we would do it. What is the slope of a horizontal line? 0. So those horizontal tangent lines would have a slope of 0, wouldn't they? So the slope of a tangent line, that's dy dx, right? That's the derivative. And for us, our derivative, our f prime, is right here. So what I would do to find the exact locations of these horizontal tangent lines is I would set f prime equal to 0, right? Where's the slope of the tangent line? 0. Bless you. Just set the derivative equal to 0. So that would be 3x squared minus 9 equals 0. And then we just solve that. So take 2 seconds real quick and solve that. We should get 2 answers, right? You guys all thought that there were 2 answers, and you're, of course, correct. When you add 9 divided by 3, square root, what do you end up with?
Positive and negative is root 3.
Plus or minus the square root of 3. Yep. So we were guessing plus or minus 2. And isn't root 3 pretty close to 2? It's like 1.7, I think. 1.7 dot, dot, dot. So 2 plus minus 2 was a reasonable guess for sure. All right, how we doing? Tangent lines. Tangent lines will just keep coming back over and over and over again. So definitely an important thing for us to be good at. All right, so let's move on. Let's talk derivatives, and maybe I'll like sort of informally prove one to you. So the derivative of sine, has anybody read ahead or know this from somewhere else? What is it, Mandy?
Cosine?
It's cosine. Yeah, the derivative of sine is cosine. Like I said, we can look at kind of a basic proof of this in a second. And the derivative of cosine is negative sine of x. Yep. So if we wanted to prove this using the definition of the derivative, we'd have to do the sum identity. Sum identity for cosine or sine. Sine of a plus b is what sine a cosine b plus sine b cosine of a, I think it is. We're not going to go there. I'm going to use a graph to kind of prove it to you. So let's do this. I'm going to set up a graph with, I'll tell you what, I'll put sine. Let's do this. I'll put sine on the graph. So in red we have, oops, sine. Look good enough? Here's my graph of sine. And what we're going to do is we're going to graph its derivative. So we did this the other day, right, where we take a graph of f and we graph f prime. Okay, so let's try to do that again. This will be a good exercise, perhaps. The first thing we always want to do is we want to find places where f prime is 0. So how many places do you see where f prime is 0?
2.
Another way to ask this would be how many horizontal tangent lines do you see, right? And there's 2 of them, right? So right here is a place, and right here is a place where the tangent line is horizontal, therefore f prime would be 0. So when we go to graph f prime, where would we put those 2 points?
X-axis.
On the x-axis, right? So right here and right here. And then once we've done that, we're just going to split it up into little intervals. So I would look at it and I would say on this interval right here, the slope of the red graph is pretty clearly positive, and so we would graph f prime where? Above the x-axis. And so, start up here somewhere, but we know we got a curve down to that, right? We got a curve down to the 0. That makes sense? Okay. So then this interval right here, from roughly here to roughly there, the slope of the red graph is pretty obviously negative. And so when we graph f prime, we're going to put the f prime graph where? Below the x-axis. Yeah. So I do have to curve back up to hit that other 0, so it'll look something like that. And do you see what's starting to happen? Yeah, we're graphing cosine, because you look at this final little interval here, the slope of the red graph is pretty obviously positive, and so we would graph f prime above the x-axis. It looks something like that. So you can see the green graph is actually cosine, and we got that by differentiating sine. And so again, no way does that proof hold up under scrutiny. We're just looking at a graph, right? We could do the double angle identity or the sum identity if we wanted to, but I think a graph is kind of an effective way to look at it. So there you go. Do you have any questions? Okay, let's see. Oh yes, sir. Go ahead, Jonathan.
So if we were asked, like, on a test to, like, graph the f prime of cosine of x, or I guess sine of x, and we didn't draw it like cosine because we know like what the graph is supposed to look like. If we drew it just like really awry but still like hit all the points and stuff.
Oh, yeah, that'd be fine.
Okay.
Yeah. Yep. And if I don't think I would give you a specific label for the function and say this is sine and then ask you to do that. So I'd still just be looking for those 3 key ideas. The zeros, the positives, and the negatives.
Okay.
Yeah. Titus.
If you ever asked us to like graph the derivative of something, can we just
like do the power rule and graph that?
I would be very careful with that, not because it's wrong, but because you could get yourself all twisted up into thinking, what does this graph, the derivative, what does it look like? To me, it's easier to just say, where are the zeros, where is, positive, negative on f prime. To me, that's easier. Your thought is not a bad thought, and it probably would work in every case, but to me, it feels like a longer, more gangly approach, because if you're like, hey, that's a quartic, so its derivative would be a cubic, then the next thing would be like, okay, where are the zeros on this cubic? And I'm thinking to myself, just find the horizontal tangent lines and go bam, bam, bam. But your strategy would certainly work, no doubt, no doubt. The crazy thing is a lot of the graphs that I'll give you are none of the above as far as polynomials, right? Because I could give you one that has like crazy curves and then a sharp point, piecewise stuff, and that's where that sort of thinking is kind of like, if you've only relied on that thinking, you're going to be like, oh my gosh, what do I do with that? But your strategy for a nice polynomial would definitely work. Great questions. I love what if questions. Keep asking them. Anybody else? Okay, cool. So let's go ahead and use those skills on numbers 9 and 10. But before we do number 10, let's talk about some really important algebra that may or may not be easy. We'll find out. Let's manipulate number 10 a little bit before we do the derivative here. What do you think we should do, or what do you think we should do with that first term, 5 over parentheses 2x cubed? It's not in a good place right now. Caroline, what do you think?
Bring the 2x cubed up to the top.
Okay, so if I did that, it would be 5 times parentheses 2x to the, not 1/3, negative 3. So I like your idea, but I think it's maybe one step early. Because if we took this to its logical conclusion, wouldn't we get this? And that's not a bad thing at all, but a lot of folks are going to have an issue with, what do I do with that? Maybe, or even maybe they wouldn't even get that. So maybe we'll see, your strategy could definitely work, but maybe we'll see how we kind of come back around to that in the end if we take a slightly different strategy, just ever so slightly. So let's not do that. Is there something else you guys can think of? What could we do to simplify this a little bit, get it into a better form? Go ahead and do the exponent, right? So what's 2 cubed? 8. So it would be this. So y equals that. And then I would suggest one more thing, and this would be where we finally get around to what you were saying, which was a good strategy. We don't want the x in the denominator. So how do we get it out? Negative exponent, flip it, right? So it would be y equals, I would write it exactly like this. 5/8 x to the negative 3 plus 2 sine of x. A lot of times people will find the algebra to be just as difficult, if not more so, than whatever calculus is coming next. So I wanted to show you guys that. So let's do number 9. Let's do the derivative for number 9 and do the derivative for number 10. But I wanted to kind of show you that algebraic manipulation before you did number 10. All right, Caroline, your question. Okay, Maddie, do you have number 9?
Please don't trust in my.
Hey guys, listen up, please. Maddie's going to share her answer for number 9. What do you got?
I just did pi times negative sine of t.
Pi times negative sine of t. What do you guys think? Is that fantastic? Yes, it is fantastic. Definitely. You could write it slightly differently. It would have absolutely no difference in meaning, but you might write it as negative pi sine of t. Just flip the order around there on the negative and the pi, but it makes no difference that what she wrote there, what she said is correct for sure. Okay, how about number 10? Have we gotten that one?
No.
Not yet? Okay, keep working. Keep working on number 10. Think of it as 2 separate problems, right? There's the first term, there's the second term. We kind of deal with them separately. So can we do the first term first?
Yeah.
The first term is a power rule, right?
Yes.
It's basically a version of like x to the n, that derivative. And so kind of like we were talking about earlier with Doug, is going to do the exponent thing, blah, blah, blah. So Tyler, what did you get with the first one, the first term?
Negative 15 times x to the negative 4th.
You handled that really, really well. Exactly right. It's tempting to make a little mistake with that negative 3, but of course when you subtract 1 from negative 3, you do get negative 4. So Tyler, nice work. Now the second one. and we'll dig deep into this in a second here, Mandy, because you asked a really good question. Do you guys, any volunteers? Derivative of 2 sine of x. Don't be shy. Chloe, how about you? Go. What'd you get?
No, but that's something else. Oh wait, I was gonna send it to you.
Chloe, just throw it out there. We all know you're either going to be right or wrong, and it's okay either way. Right? It's okay either way. 2 cosine x. Well, that was terribly awesome. Well done. I was trying to mess with you there a little bit. Okay. So here's the question. Mandy put a good question out there, and I don't know if the rest of you guys had this question. She said something along the lines of, I see that this 2 is right here. I understand that 2 is a constant, and the derivative of a constant is 0, right? The derivative of a constant by itself is definitely 0. But I would say that, we realize that 2 is a constant. I would call it, in this case, a constant multiple, right? Because isn't it 2 times something, right? And something happens to be sine of x. So the constant multiple rule basically is this. Let's just focus on 2 sine of x for a second. What we do with that, when you have a constant multiple, 2 times an x, 2 times a sine of x, 2 times some variable, what we actually do is we ignore the constant multiple. We just totally ignore it. And then we do the derivative of whatever the other thing is, and then in the end we multiply the 2 back in. Right? So this is the constant multiple rule. And so you would say, all right, well, I'm ignoring the 2. The derivative of sine is cosine. And then we remember, oh yeah, the 2 is actually in there, so we multiply it back in after we've done the derivative. That's technically what's going on. You'll get to a point where you get really comfortable. You just mentally ignore the 2, and it all flows for you pretty well. But that's really what's going on. Yeah, Tyler.
So if it's like sine of x over 2, would you do the same thing?
I'd say it's 1/2 sine of x, right? So I'd mentally pull that 1/2 out and do the same thing. Yep.
What if it was like sine squared of x? Would it just
That's
be,
totally different. That's not a constant multiple. That's an exponent.
what would you do for the derivative?
Something called the chain rule.
What is it?
We'll get there soon. We'll get there soon. Okay. So guys, we need to conclude. This this section here and get ready to move on. So here we go. Rates of change. This is review. The derivative is the instantaneous. So we'll put INST for instantaneous. Derivative is the instantaneous rate of change. Now this next one, I don't know, maybe you know this, maybe you don't. If you've had a physics class, you probably do, or it's somewhere in the back of your brain somewhere. Average velocity is equal to blank over blank.
Change of distance over change in time.
I'm going to tweak that just a little bit and say change in,
Displacement.
change in position, which is displacement, right? So we're going to call this displacement. Displacement, like I said a second ago, is really just change in position or change in location. And then velocity, if you divide by change in time, you end up with average velocity. Think about displacement like this. I'm assuming you woke up in your house today, right? You woke up probably specifically in your bed. Hopefully you didn't wake up, on the side of a mountain road somewhere, but if that's the case, maybe we should talk. If you woke up in your bed, and then later on tonight, maybe you go to the football game, or maybe you go out and have dinner with some friends, or you go home and spend some time with your family, or whatever it is you do, at some point tonight, aren't you probably going to end up back in your bed? And so really what you would say, listen carefully, there's a point to this, what you would say in a case like that is, if you started in your bed, and then you ended in your bed, your displacement for the day is? 0. There is no change in location, is there? 0 displacement. That doesn't mean that you didn't travel. You obviously had some distance that you traveled, because you're here now. But your displacement would be 0, right? So displacement is specifically change in location. What is the difference between your starting point and your ending point? So we could actually write a little formula based on that. So let's write on the or, let's write another fraction. Displacement being the change in position. How could we write that as a formula? I go x2 minus x1, x1 minus x2? Sure. We typically write x2 minus x1. That is your change in location, right? I was at x1, now I'm at x2. To find the difference, I subtract them.
Would you have to do the absolute value of that?
Nope, because we're talking about displacement. Displacement actually is a vector. It could be positive or negative. So then delta t, we could expand that similarly. We could write it as t2 minus t1, right? Change in time. That makes sense? Change in position over change in time is your average velocity. That word displacement is actually used in the new framework, and we'll talk about it quite a bit as we move on, so just so you guys know. Let's take a look at our first example here. having to do with a billiard ball. This is a somewhat terrifying example, right? Billiard ball being dropped from 100 feet could do some serious damage. Don't be under it. Here we go. A billiard ball is dropped from a height of 100 feet. Its height s at time t is given by the position function s equals negative 16t squared plus 100, where height, or s, is measured in feet and t is measured in seconds. If you've had physics, you maybe recognize this a little bit, right? Kinematic, kinematic there. The one thing about this is you guys are used to gravity being negative 9.8 meters per second squared. It still is. These are English units though, feet and seconds, and so feet per second squared for gravity is actually negative 32 feet per second squared. So that's why it looks a little bit different than maybe what you're used to. But here we go. Let's use this information to help us with this one question. Find the average velocity over the time interval 0 to 2. And that's this formula right here, isn't it? Average velocity, change in position over change in time. So let's adapt this specifically to our question. What do you think? What could I put in there for x2? 2. I don't think position 2 is 2. No, I'm not being silly. I think time 2 is 2, right? So I think we probably could put this right away. We could say average velocity equals something over 2 minus 0, right? Because time 2 is 2 and time 1 is 0. So I think we could go there.
And then plug those into the equation to figure out the position.
Exactly, yeah. So how about we write s of 2 minus s of 0? Right, and we can do stuff with that, but you could write it like that. So take a moment, let's figure out s of 2, let's figure out s of 0. Okay, ready to go. What are you guys getting for s of 2?
46.
Say again, Macy? I think it's 36, yeah. 36 minus s of 0, that's the easier one, isn't it? What's s of 0? 100, okay. Riker, did you get a final answer yet? Okay, keep going. That worked out? Good. You even got the right units there. Nice job. It's easy to write M instead of
Yeah, I
that.
know. I had to think about it before I heard it.
That's what we're used to, for sure. Natalie, did you get it yet? What'd you get?
Negative 32 feet per second.
Negative 32 feet per second. She included the units there, which is great. We'd want to do that. And she used the right units, right? Feet per second as opposed to submetric unit. And we will use metric units too. It just so happens that this was feet in seconds instead of meters in seconds. So, all right. We good? Okay. So let's see if we can take a little bit of a turn towards calculus. So let's see if we can go through some of these little fill in the blanks. First statement says average velocity is the average rate of position change between two locations. So instantaneous velocity would be the instantaneous rate of position at a single point in time, right? In other words, to find velocity, take the derivative. Yep, take the derivative. I'll just put deriv. Take the derivative of the position function, and you can see that little formula highlighted in yellow right there. Velocity is equal to s prime. V is equal to s prime. And so that would be describing the relationship between velocity and position functions. Just differentiate position to get velocity. We'll do an example with that right now. Question A, the billiard ball being dropped. But this time part B is worded a little differently than part A. Part A said find the average velocity. Part B says find the velocity of the ball. What's that next word? That's a pretty important word, right? Because now we are not talking about average velocity. We're talking about instantaneous velocity at a single point in time. So, in order to do this, I need a velocity function. What do I need to do, Ashley? Because I definitely don't have a velocity function, right?
Yeah.
What do I have?
You have S, you have S prime.
I've got to find s prime. That's exactly right. So, Ashley, let's practice this. What is what is S prime?
It would be negative 32 t, and then plus 0.
Plus 0, right? Because that 100 is just a constant, right? And so the derivative of a constant is 0. So yeah, negative 32t, that's it. So that would be the velocity at any time. We want to know the velocity at 1.25 seconds. So what do we need to do to find that? Plug it in. That's right. So I'll write something like S prime of 1.25 equals 32 times 1.25. Do a little multiplication. What'd you guys come up with? Should be, or yeah, I lost my negative. Oops. Let's fix that. Negative 40. What kind of units on that? Feet per second, yep. Okay. You guys good? Okay. Let's take a look at our diving board question. Yeah, let's do the diving board question here, and we'll be done with 2-2. If you're an auditory learner, listen or read, Here we go. At t equals 0, a diver jumps from the diving board that is 32 feet above the water. The position of the diver is given by S of t. You can see it right there. S is measured in feet, t is measured in seconds. Find when the diver hits the water. We'll do that first. And then find the diver's velocity at impact with the water. So let's look at that first question there. Find when the diver hits the water. Any thoughts on a strategy there? Find when. So what kind of a question is when? Time. So find the time when the diver hits the water. What do you think about hits the water? What does that mean? What is 0? The height. The height is 0. So what could I do? Okay, so solve which quadratic? Set equal to 0. There you go. So we would just write something along the lines of 0 equals negative 16t squared plus 16t plus 32. And solve that. What would you guys do if you did not have a calculator? Factor. What would you factor? I think a 16 would be a good thing to factor out, or really, since it's an equation, you could just divide. But let's be a little more specific. How about negative 16? Let's divide everything through by negative 16. That will give me 0 equals t squared minus 2t, or minus t, excuse me, minus 2. It goes from sort of complicated to a lot less. Mark, what do you think about a factoring here?
Well, it's negative 2 and 1.
Okay,
So,
yeah. T minus 2, t plus 1. So then for our times, we would get t equals 2, t equals negative 1. Which one do we ignore because it's a guy diving off of a diving board? Negative 1, right? He's not going to hit the water 1 second before he dove. Right, it's a little bit weird, right? Not going to happen. So the t equals 2 makes sense. So I'm going to let you guys run with the other part here. It says, find the diver's velocity at impact. See what you can do with that. We just practiced this a second ago. Okay, so S prime of 2 equals negative 32 times 2 plus 16. So what is that? Negative 48? So S prime of 2 is negative 48. And what units would go with that? Feet per second. Awesome. Okay, so that's kind of that first little relationship between velocity and position. You have any follow-up questions of any kind? Okay, so this is where we want to go. We need to get into 2.3 here for sure today. So let's flip over to that and see how far we get. Little saying for the product rule. 1d2 plus 2d1, yeah. So, like I mentioned in the video, I think that it's worthwhile taking a second to identify what your 1 and your 2 would be. So, it really doesn't matter which is which. I usually just call the first one number 1 and the second one number 2. But you could flip those around for whatever reason. It's up to you. Not a big deal. All right, so let's give this a shot. What does 1 mean? Like 1d2 plus 2d1, what does the 1 mean? Yeah, just like write the first factor, right? Just write it down. So here we go. F prime of x equals 2x cubed plus 4. And then d2, what does the d mean? Do the derivative. So what is d2 for this one? Cosine of x. Very good. So that's 1d2 plus 2 just means rewrite the second one. Are you good, Pristine?
Why is there not an X on the 4?
I have a good answer for that. You know what it is? I just forgot it. It's okay to ask that question. Every now and then, a seemingly otherwise capable person will just lose something, and that's what I just did. Sorry. So 2x cubed plus 4x times cosine of x, so that's 1d2, right? Plus 2d1. So what's 2? Sine of x, right? And then d1 is where we got to do a little bit of work. McKenna, what do you think about d1?
6x squared plus 4.
6x squared plus 4. Nice work. Okay, so if all we were asked to do was find, this is something a lot of folks get uncomfortable with, but in all honesty, if all we had to do was find f prime of x, you could leave it just like that. Because at that point, haven't you done it? Anything else beyond that is just algebra stuff. And maybe it might be beneficial to do that, but if all I said was, hey, find f prime of x, you just did it. There's no reason to put it in any other form unless you're compelled to do it for whatever reason. So I would leave it like that. But we do want to find f prime of 1 here is what the question actually asked. And so, Riker, what does that mean? F prime of 1, we do? Plug in a 1, yeah. So we can do all this arithmetic in our head. If you plug in a 1 to that 2x cubed plus 4x, what do you get? 6, yep. So 6 cosine of 1 plus sine of 1 times what? 10. Yep. If you've got a calculator, you would have taken a little bit of a different strategy here. Your calculator will do a lot of this heavy lifting for you. So let's just pretend like we didn't have a calculator, and wouldn't we have to leave it like that? Anybody know what cosine of 1 is?
1.
Me neither. No, cosine of 0 is 1. Cosine of pi is -1. Cosine of 1, who knows what that is, right? Who cares? We don't have a calculator. Let's move on. All right. Why don't you guys try number 3 by yourselves? This is a little more symbolic. In a lot of ways, it's a whole lot easier, but in some ways, it's tougher. So let's see what you do with number 3. Gives you some information about f prime, and then it tells you that h of x is equal to cosine of x times f of x, and then it asks you to find h prime of 2. So let's see if you can apply the power rule, or excuse me, the product rule to this situation. So in number 3, would it be fair to say, on some levels it's easy, and some levels it's very difficult? It's very conceptual. Let's see how we did.
So it's,
Could you talk just in a more quiet voice?
oh, sorry.
Thank you. Unless you want to be recorded forever. Here we go. So number 3, it gives you information about f, it gives you information about f prime, but then really right here, this is where kind of you start. H of x equals cosine of x times f of x, and it wants to know h prime of 2. To find h prime of 2, you got to find h prime of x first. So, guys, again, could you talk a little more quiet, Titus? Thank you. Okay, so here's what I want you guys to notice. H of x equals cosine of x times f of x. What does that mean that we have to use? You have to use the product rule. Product rule is not like an optional thing that sometimes you do it, sometimes you don't, whatever, whenever you feel like it. If your function is a product of 2 other functions, you're differentiating, you have to use the product rule. So, if we're going to use the product rule, it's 1d2 plus 2d1. So we got a label. I always say this is number 1, and this is number 2. Again, you could switch it if you wanted to. So what we're going to do is that 1d2 plus 2d1. So let's go h prime, actually I'll do it over here. H prime of x is equal to, Riker, what's the 1?
Cosine.
Yep, cosine of x. What's d2? F prime of x, right? So this is one of those weird moments where it's so simple that it's difficult. The derivative of f is just f prime. All right, so there's 1d2 plus 2. Jonathan, what's 2?
2 is just f of x.
Yep. And Delaney, how about d1?
I don't know.
You're definitely a step ahead of me. So d1, I'm asking you for the derivative of number 1. So I'm not looking for a number here yet. Okay, so let's go back and think about this. So were you okay with this first part?
Yeah.
Okay, so the first part was 1. This was d2. So this was 2. And what we're looking for here is d1. So what's my number 1 function? What did I label as number 1? So what's d derivative of that? No, okay. Just for like when you think about the 1 and the 2, forget that it's in a product. Like we labeled 1 as cosine. So like number 1 is just cosine. Number 2 is just f of x. So just focus in on cosine. What's the derivative of cosine?
Negative sign.
Negative sign. I feel like you were giving me the entire right side instead of just that part. Does that make sense?
Yeah.
Okay, so 1d2 plus 2d1. Does that make sense? You okay with that? All right. So let's go ahead and try to figure out what it wants us to figure out. It wants us to find h prime of 2. So h prime of 2 just means plug in a 2. Wherever you see an x would be cosine of 2 times f prime of 2 plus f of 2 times negative sine of 2. Can we do anything else with this? Are we done? Can we do like one more little thing? Do I, like, let's say I don't have a calculator. Do I know what cosine of 2 is? Or sine of 2? No, I don't. But what's f prime of 2? Yeah, we're told that in the beginning. It's 4. So I think we could write equals 4 cosine of 2. And then what's f of 2? Negative 3. So I think we could write plus negative 3 times negative sine of 2. So if you wanted to, you could clean it up a little bit and just say 4 cosine of 2 plus 3 sine of 2. That would work just fine. I mean, that's just a little cleanup work, not necessary by any stretch. How many of you guys did that whole thing, got to the end, success, we're good? Can you just raise a quick hand? Okay, I just wanted to get a quick sense of where we're at. We're going to do a quotient rule here, and this will probably be about it. So you guys remember the quotient rule from the video? What was the little 6? If g of x equals sine of x over x. So we're going to find g prime of pi over 6. We've got to find g prime of x first, and then plug in the pi over 6 after that. So we are just a touch short on time, so let's take just a minute here. And at the very least, let's get g prime of x. Than need be. So let's go ahead and get through as much of this as we can. So low d high minus high d low over the square of what's below looks like this. G prime of x equals, what's my low? X. What's d high? Minus high? What's d low? 1. So I'm not going to write anything there. Over the square of what's below, x squared. Now, to finish this, you'd have to do some unit circle trig. So, be g prime of pi over 6. We just plug that in. So, it'd be pi over 6 times cosine of pi over 6 minus sine of pi over 6 all over pi over 6 squared. Some parts of that we're not going to be able to do without a calculator, like pi over 6 squared. But we could definitely do cosine of pi over 6 or sine of pi over 6. Do you guys know what cosine of pi over 6 is? Root 3 over 2. How about sine of pi over 6? 1 over 2. There you go. Awesome. All right, we're good. I'll see you guys on Tuesday, right? Yeah, Tuesday. Hope you have a wonderful weekend.